Hi guys, today we're going to go over chapter 15.9 AP Chemistry. It is about equilibrium, and we're going to learn Le Chatelier's principle. But before we do, I want to come over here to our simulation, and I want to show you guys a reversible reaction with equilibrium. I'm going to just raise up the energy on each side so that the difference between them is smaller, and that's going to allow it to reach equilibrium faster. Because if you have a lower activation energy, the reaction will take place more quickly, usually. Okay, there's a couple of factors involved. One of them is activation energy. So if I start with, let's start with 50 on each side. 50, enter. And I'm just going to let them do their thing and bounce back and forth while we go through the notes, and then we can come back to this as needed once it's reached equilibrium. So remember, I started 50-50, and it's going to end up somewhere close to there because they're pretty close to equal in energy. At the equilibrium, there will be a little more on the product side than on the reactant side, just because it's just a tiny bit lower, about 5, whatever these are, centimeters or whatever the measurements are. Okay. So Le Chatelier's principle said if a system at equilibrium is subjected to stress, we know something about that. Any change to the system is a stress on the system. It's going to try to relieve that stress, which is what we need to do, right? The equilibrium is going to shift. It's going to adjust itself. It's going to pivot. It's going to change something else to relieve the stress. So whatever change you make, it's going to try to undo that change in order to reestablish equilibrium. Okay, and that actually literally does apply to our lives. So if there is a stress to the system, our system, we're going to try to adjust in a way to relieve the stress and come to a new kind of balance point. Hopefully, that's the goal, right? Is balance. That's what life is all about. We got to balance our workload with our mental health and all the other things that we're balancing every day. So changing the concentration of a reactant or a product is one type of stress. Okay, so concentration is the first one we're going to talk about. That means in my simulation, I would add either to the product side or the reactant side. That would be a stress to the system. Okay, it's 45, 55, and it looks like it's staying pretty steady. So my equilibrium here would be, oh, nope, right when I said that it changed. I'm waiting for it to stop. 40, 60, okay, so it's still adjusting to reach equilibrium here. So I would put products over reactants to find my K value, and adding to one side or the other is going to put a stress on that system. It will no longer be at equilibrium. But guess what? It never stops. It's dynamic. So it's going to keep going until it reestablishes that equilibrium. Okay, so it was not at equilibrium because it kept changing, and now it's at 36, 64. All right, so adding reactants. Adding reactants, which in this generic equation is A and B, it's going to push the reaction in the opposite direction. So it shifts the equilibrium to the right, towards the product side. If I have this at equilibrium and I add A, what's going to happen? That added A is going to react faster and make B, whereas the B is still going to have the rate that it had before we added. Okay, so the rate that A turns into B would be greater than the rate of B turning into A. So that's why we say it shifts to the right. Okay, do you guys think it's at equilibrium now? It's about the same. We'll come back and check in a second. Adding product, so if I add to the right-hand side, that pushes it to the left. Adding products, C or D, shifts the equilibrium to the left. So whatever side you add to, it goes the opposite way. Removing stuff. If I come back to my simulation, yes. So if I were just to delete some of the product, what's going to happen? If we take away from the product side, then A is going to keep reacting and forming B, but there will be less of that product to unreact and reform the A. Okay, so it's going to actually start replacing what we took out. So if you remove something, taking out reactants will shift to the left where the reactants are. Taking out product, like we were just talking about, if we remove products, it's going to shift to replace those products that we removed. So it shifts to the right. Okay, now on the AP test, they're not going to ask you, does this shift left or shift right? That's too easy. It's a 50-50 chance of getting it correct. What they're going to ask is something like this. What happens to the concentration of NH3 when you remove hydrogen or nitrogen? So that's a typical AP question. To get there, let's answer the easy question first. What direction will it shift if I increase H2? If we add hydrogen to this reaction, it's going to push it the opposite way. It's going to push it to the right. Okay, so we can say it shifts right for the first part. A better question would be, like I said, what happens to the concentration of ammonia if you add hydrogen? It will increase the concentration of NH3 because it's shifting to the right, meaning more product will be produced, so NH3 concentration goes up. Okay, hopefully you followed that logic. If I increase ammonia, so if I increase my product, that's going to push the reaction to the left, and that means my nitrogen and my hydrogen will then start going up. Okay, so this one is left, that one is right. What direction will it shift if I increase hydrogen in this reaction? Well, that's going to go to the right. If I increase iodine, also to the right, because both of those are reactants. Okay, changes in temperature. That depends on the equation. I can't say for this one, oh no, I can say, what type of reaction is this? You start with a higher energy, you end with a lower energy. That's going to be an exothermic reaction. So in other words, this much energy, so about 5, let's say it's joules or kilojoules, 5 kilojoules are going to be given off. So this is an exothermic reaction. Something like this right here. So nitrogen plus hydrogen making ammonia gives off 92 kilojoules is a product of that reaction. This is going to be exothermic. Exothermic. And think of the heat coming out as a product of the reaction, and it makes this a lot easier. So if you are increasing the temperature, what you're doing is you're adding heat. So if I add to the product side, that will shift it to the left. So for exothermic, an increase in temperature pushes that reaction to the left. For endothermic, so this reaction right here, the second one, 510 kilojoules are needed to go into the reaction in order to make my products, hydrogen and oxygen. So if I increase the heat of the second reaction here, I'm going to shift this to the right. So for an endothermic reaction, an increase in temperature will push the reaction. It will allow more water to unreact. So let me talk about what this is really quick. Hydrogen and oxygen can come out of water. So basically what we're doing here is we're decomposing the water. We're taking water, adding energy to the water, usually by electricity. So we put 2 electrodes in there, and run the electricity through it, so we add energy that way, the water will break down into hydrogen and oxygen gas. And think about this. If it's at some kind of balance point where they're both happening, the hydrogen and the oxygen are then reacting to form water. Adding heat is going to allow more water to actually separate. Okay, so that's going to shift it to the right. An increase in temperature would push this second reaction to the right. Versus this one, an increase in temperature will push this one to the left. Okay, hopefully the concepts behind it make sense, because you're not going to be able to memorize. You just have to be able to look at what direction it's going to shift based on what we know about that equation. Okay, and let's see if that's true. Yeah, let me see if that's true. So we are at equilibrium now. Let's say it's 3565. So my equilibrium point, 3565. Come on. So K is B over A for that reaction in my simulation. And I said we had 60, does it go back to 65? I'm going to say it will eventually return to 65, 35. So 65 is my B, 65. If it's not exactly these numbers, it's pretty dang close. Okay, 65. Since the coefficients are both 1, we don't have to raise it to any exponent. It's 1.86 is my K value. So it's telling me that this reaction lies to the right, meaning the products are favored. Products are favored. And yep, okay, it went back. So if I increase the heat, since this is an exothermic reaction, adding heat to this mix, heat's coming out, should shift it to the left. So I should end up with more A. Let's see if that works. Let's heat that up. It's about 170. Let's change it to like 300 Kelvin. And see. It might need some time to adjust itself. Okay, they should all be moving faster. Oh, there we go. So now you can see it's about 40-60. What's going to happen? It's going to cool back down if I don't keep adding heat to it. It's going to cool back down and reestablish that initial equilibrium. But right now, in the meantime, notice that I have decreased the amount of B and I've increased the amount of A. So I have added a stress to the system and I've forced it to shift to my reactant side. And it's already going back down. Okay. So that's temperature and concentration. Changes in pressure. Pressure does not affect liquids or solids since the atoms are already touching. They can't really get any closer than that. So it only affects gases. The total number of moles of gas on the left must be different than the moles on the right. Okay? More pressure. If you increase the pressure on your reaction, it's going to try to relieve that pressure by taking up less space. So the little molecules inside want to take up less space. That means fewer moles. Shifts to the side with fewer moles of gas. And less pressure, if you allow the gas in your reaction to expand, so you reduce the pressure on the system, it's going to try to fill up that space by shifting towards the side with more moles of gas, because more moles of gas take up more space. So shifts to more moles of gas. Okay, so for example, if we increase the pressure on this reaction right here, if I put this equilibrium under a stress of condensing it down, it's going to shift to the side that takes up less space. Well, there are 4 moles of gas on the left, and there are 2 moles of gas on the right. So the products take up less space. They have fewer number of moles than the reactants do. So increasing the pressure would cause this one to shift to the right. Okay, for the second example, water decomposing into hydrogen and oxygen, an increase in pressure of that one will actually shift left, because there are 2 moles of gas on the left and there are 3 moles of gas on the right. So that one's going to shift left. What about down here? This solid does not count for pressure. So I have 6 moles of gas on the left, 12 moles of gas on the right. An increase in pressure will cause this reaction to shift to the left. And last but not least, this hydrogen plus iodine makes hydrogen iodide. If I increase the pressure on this system, what happens? It's a trick question. There's 2 moles of gas on the left and 2 moles of gas on the right. There will be no change to the equilibrium. They will all just become closer together, but you're not going to have a shift in the number of products or reactants. Okay, and then to finish up the notes, a catalyst will speed up the reaction initially, so you get to equilibrium faster, but it has no effect on the actual equilibrium or the equilibrium constant. It just gets to the equilibrium faster. All right, have a great day, and I'll see you guys tomorrow.